I introduce our speaker, I would just like to remind you of our next lunchtime talks in science and math is going to be Wednesday, March 18th. So in 2 weeks, it's going to be Dr. Robert Estalos, talking about some of the stuff that he did at the planetarium for his sabbatical. So this week we have Dr. Aldrich. He's full professor of math here, and I'm not sure what he's going to be talking about. It's a mystery, I guess, but let's give him a round of applause.
Thank you all for coming, and I think I should start off by thanking Dr. Naring in absentia. We should all thank Dr. Naring. He has been running this lecture series for 11 years. So thanks, Dr. Naring. And before I get started, I'll just tell you a quick story about what happened to me last night. I was sitting in my house. I was working on my talk, really excited about what I'm discussing this afternoon with you. And it got kind of late. I said, well, maybe I should shut things down and take a break, see what's on the tube. And my Kentucky basketball team is playing. I forgot completely all about their, what is it, their 29th, 30th in a row victory. Anyway, so I turned I turned the TV on, and it's like the last 2 minutes of the game. Whoa! So that's how much I was interested in what I'm going to talk to you about today. So here's a brief outline of what's going to happen. We're going to have a very brief introduction to modern algebra, and we're going to be looking for a theme. A very brief introduction to topology, and we will be looking for a theme. We will look at somewhat of a marriage between algebra and topology called algebraic topology. And then this slide here really is for Dr. Estalos, because he's the one who would say, well, who cares? Where can I actually use this stuff? So we're going to start with modern algebra. And as often happens in modern algebra, you're going to restrict your attention to a small collection of numbers. The first collection of numbers we're going to be interested in is just the numbers the collection is the numbers 1 and -1. We're going to investigate what happens when we multiply them in pairs. There are only 2 numbers there, but you could choose the same number twice if you wanted to. For example, we could choose the pair 1 and 1 and multiply them together. Now, I'm not trying to trick you. 1 times 1, at least for now, is still 1. But there are other possibilities. You could choose -1 and 1. Again, I'm not trying to trick you. Okay, good. We're all on the same page as far as multiplying 1 and -1 together. There aren't a whole lot of choices, actually. You can multiply -1 times -1. All right, we're cooking with gas here. We have 1 and -1. You multiply those together and you get -1. And what we could do with this information here is summarize it in a table. There are only 2 objects that we're discussing. Let me put them like this. So 1, -1, and then 1, -1. And this is a very small times table. When I write this table, I'm going to think of the number on the left, which is signifying the row, is first, and then the number on top is signifying the column, and that's second. So whatever goes here is going to be this number times that number, and we already calculated these, so I'm just going to fill out the table. So one of the things that we can see about this is when you take the numbers 1 and -1 and multiply them in pairs, you're only going to get those numbers back. So it's not just that I restricted myself to using those numbers in the products over here. The results are still those numbers. There is some symmetry to this table, which is nice. There's symmetry along this main diagonal here. You see that this number here has a mirror image along that diagonal over here. Another thing an algebraist would be interested in is realizing that every number in our collection has what we call an inverse. So first of all, look at the row corresponding to the number 1. The row corresponding to the number 1 is just a copy of that row on top. Flip that over and look at the column corresponding to the number 1. The column corresponding to that number is an exact copy of that column. So in this collection of numbers, you have a number When you compare it with the other numbers in your operation of multiplication, it doesn't change anything. You do have this other number, though, -1, and when you multiply it by itself, you get 1. So in a sense, when you multiply those two numbers, they cancel each other out, and you get the thing that doesn't do anything. So you have one thing that's kind of boring, doesn't change anything, and you have one thing that's different, it's -1, and it changes the ones. Notice that -1 times 1 is -1. It also changes this one, but then when you put it together in a pair with itself, it cancels itself out. So we would summarize this as saying the set containing -1 and 1 forms a group under multiplication. You don't have to worry about that. That's just some jargon. I will be using that jargon for a little while. We can change the process by adding new numbers to the system. So I started with 1 and -1. You might have been here last week for a discussion on the complex numbers where we had the letter I representing the square root of -1. Now this is a weird square root because theoretically you're not supposed to be taking the square roots of negative numbers. Let's just pretend that we can and see what happens. This is going to behave like any other square root you've encountered before in the sense that when you multiply it by itself, you have two square roots that are being multiplied. The square roots cancel, and it's -1. Now the reason why this is surprising is because you're not used to having squares being negative. So we're going to investigate the powers of I, and by that I just mean I'm taking I, square it, you get this number, which, by the way, is over there. You can raise I to the third power. There are a variety of ways you can calculate this. You can do I times I, which is the long way. You could also realize you just did I squared, and you can use that. So this is going to be something like I squared times I. We just make a substitution. I squared is -1, and so I cubed is -I. You can keep going. Again, you don't have to reinvent the wheel every time. I to the fourth technically means I times I times I times I, but you just did I to the third, so let's use that. I to the fourth is I to the third times I. We substitute that in, what you get is -I times I. The interesting aspect here is that we got rid of two of the i's, but we still have two of them. So let me go ahead and rewrite this as -I squared. I squared is -1, so this is -1. And -1 is 1. I'll try one more. I to the fifth. I to the fifth would be I to the fourth times I. I just came over here because I ran out of space. We just did I to the fourth. I to the fourth is 1. Multiply that by I. Again, I'm not trying to change the rules here. 1 times I is still going to be I. We've encountered what we describe in mathematics as a cycle. When you take the number I and start raising it to powers, you get some different things for a while, but then you get back to where you started. We started with I, and by the time you get to the fifth power, you're back at I. There's a reason this is happening, and it's because I to the fourth is 1. In the sense of this table, then, I squared cancels I squared. There's a reason. This is I squared. Is everybody with me so far? You can actually use this to calculate very large powers of I very quickly. For example, we could do I to the 2015. Remember what I to the fourth was. I to the fourth was 1. If you take 4 multiples of I, or take I and multiply it by itself 4 times, they all cancel each other out, you just get 1. Well, you can do that as many times as you want. So really what we're looking for is a power of 12 close to, power of 4 close to 2015. 2012 is close. It's a power of 4. Notice that 2012 plus 3 is 2015. These 2012 i's did just cancel each other out because it's a multiple of 4. You get I to the third, which we already calculated as negative I. Okay, so I want you to use your brains. I know it's tough after eating pizza, but we're going to try it. Suppose that I know I to the fourth is 1, I to the third is negative I squared is negative 1, and I is this thing. This would be also known as I to the 1. Follow your pattern backwards. What's I to the 0? I to the 1 is the square root of negative 1. I to the 0, you have to follow your pattern by going to the bottom. I to the 0 is 1. Now, actually, that should jive with something else that you've learned. You raise a number to the 0th power, it should be 1. So there's no surprise that I to the 0, which I didn't write, but I could, is 1. But there is something interesting here. You can use this for negative powers as well. Negative exponents, when you're learning what they mean, they're asking you to take the reciprocal of something. So I to the negative 1 is asking you, flip that number over. But we know what it is if we know our pattern. You can do that for large negative powers as well. Tricky part there is you have to go backwards, and let me summarize some of this information. I guess what's happening here is my table wasn't big enough, because now there's an I, and there's a negative I. Same here, and same here. When you multiply them together, though, you're only going to get some of these other objects. For example, I times 1, that should be I. Negative I times 1 should be negative I. Negative I times negative 1, okay, cancel the negatives. And you can fill in the rest of the table. I'm not going to mess with that. Essentially, what's happening here is we added another number into our system, I. By adding that into our system, we also had to add the number negative I, because we got it just when we started multiplying stuff over there. But the end result is there are only 4 objects now. This is considered a different group. We have 4 things instead of 2. We can summarize that information by saying that this collection of objects forms a group under multiplication. In our first example, we had 2 numbers, and that was it, plus or minus 1. Second example, we had 4 numbers. That was it, plus or minus 1, plus or minus I. In algebra, we would describe those as small groups. There are large groups. One example is something that we call C star. C star is some hidden notation. Star in mathematics mostly just means, not mostly, but often just means throw 0 away. So C star is going to be all complex numbers except 0. I'm going to throw 0 out because you're not allowed to divide by 0. If you were here last Friday, there was a talk about the complex numbers. The complex numbers form a plane. We think of the real part as being the horizontal axis and the imaginary part as being the y-axis. And all I'm doing here is kind of deleting the center, saying throw that point away. And in the complex plane, every complex number that's not 0, so here's an example of a complex number that's not 0. This could be something like maybe 1 minus I. 1 minus I is a complex number. It's similar to these numbers here, except for it has both a real part and an imaginary part. But in terms of the process of multiplication, you can multiply by 1 minus I. You're going to get new numbers when you do that. But you can also divide by 1 minus I, and you're going to get new numbers when you do that. We summarize that information by saying that C star forms a group under multiplication just like these other ones did. The prototype really for groups is what we call the integers. The integers are all of the counting numbers, 1, 2, 3, 4, 5, 6, etc. Include 0 because that's the one that doesn't change anything. When you add it to other numbers, it doesn't change them. You have to put in the negatives as well because you want to be able to add and you want to be able to cancel the addition. So really what I'm doing is thinking of a negative number as being something that cancels a positive number. So from now on, that's going to be our prototype. The integers, we're going to look for that. The integers form a different kind of group, though, because the first 3 examples were groups under multiplication. And now I'm changing the structure. I'm saying don't multiply. I want you to add. So what's the theme? The theme is that modern algebra, we want to classify structures. We're going to study these structures. We're going to look at what are the objects in them. They could be numbers. They could be other things. We call them the elements of the structure. How can the objects be combined to make other objects in the structure? And that operation of combining them could be multiplication, could be addition, subtraction, could be other things. There are lots of operations. And then is that structure different from the other structures that you've seen? So just looking at the first couple of examples, we had a group with 2 objects, we had a group with 4 objects, then we had a really big group, C star, that has literally an element in this group for every point on this plane, of course, except for that one point that I had to throw out. So some groups are small, some groups are big. Sometimes the size of the group can be used to determine what its structure is. Sometimes the structure isn't determined by the size and you have to know more information. There's your very brief introduction to modern algebra. Topology is different from algebra, thankfully, otherwise why would we use a different word, right? Now last week we had a talk about flatland, and if you were here for that, that's great. I'm not going to ask you to forget the information you got from that talk, but I'm not going to be interested in what it's like to live in flatland. I'm going to be as interested in flatland itself. So flatland, I'm thinking of this as an infinite plane. It's hard to draw an infinite plane. So what I do instead of drawing an infinite plane is I draw this thing, which is mimicking a plane, and then I just say, well, keep going that way, that way, that way. It just keeps going. Now I have to wave my hands because I can't draw that. Now what I want you to do, though, is think, okay, I'm here, I'm in the plane, and I want to know what's going on around me. One thing I could do is maybe make myself a little bit of a map. Say, here's where I am, and if I go this way, something happens. If I go over there, okay, there's that, and then I go over there. And then I have this little map telling me the local structure of what's happening on this surface. So flatland is one example of something you would be studying in topology. It is an infinite plane in the sense that it extends in all directions, but you have to imagine this plane because you don't see in 2 dimensions. You see in at least 3 dimensions. I say at least 3 because some people argue that time is a dimension. I don't know if you can see in time or not. So if you can't, that's okay. You're probably seeing in 3 dimensions like I do. Other people can see in time, and that's good for them. So here's what I'm trying to suggest to you. This is an idealized structure. You just have to pretend that this thing exists. Now, I can give you a mathematical model for that object. But the discussion of what it is and what happens in there is really a theoretical discussion. So what you could do then is say, okay, well, I was here and I mapped the area, and then I'm going to go over here and I'm going to map that area. And then I'm going to ask, okay, oh, hey, you were over there. What happened over there? What was your map look like? And then what was your map look like over here? And then you can try to put all those maps together. And you can imagine it would be a challenge to map this whole thing. You have to imagine that. So just imagine that. So flatland is called flatland because it's flat. There are lots of things in topology that are not flat. Here's an example of something that's not so flatland. I'm calling it not so flat land because this is an idealized topological structure. You're going to take a sphere and you're going to remove the center of it. You're going to be looking at the boundary of that sphere, which is what we call the sphere. So you take a ball, you remove the interior of the ball, and you just get that spherical shell, but it's infinitesimally small. And the hard part is you have to imagine that those are the only points in your current universe. So we all know that there are more because we see in 3 dimensions, right? There are points over here and there are points over there. So it's really an imaginary thing. You just have to imagine that that sphere is all that exists. And you could live on that sphere, potentially, if you were a 2-dimensional object. I don't want to do it on the edge. So let's pretend that this point is on the sphere, and you could say, okay, I'm going to figure out what's happening on the sphere. What I'm going to do is the same thing I did up here. I'm going to go out in my general area. I'm going to make a map. I'm going to take that map, and I'm going to do the same thing over here, make a map. I'm going to start putting the maps together. There's a big difference between that one and that one. This one, if you wanted to map the whole thing, it would take you forever. But this one, if you wanted to map the whole thing, it wouldn't take you forever, right? Eventually you get back to where you started, you put all the maps together, and there you are. So the idea here is you want to map your local area and then see if you can put those maps together into the big picture. So I want you to imagine you're going to do that. It's kind of hard to see this. Does anybody remember which lights? There we go. What you're looking at is, this is hard to think about, especially after eating pizza and the lights are off. This is a 2-dimensional visualization of an imaginary 3-dimensional object. I say it's imaginary because this is computer generated. It's a 2-dimensional representation because you're looking at a flat screen. What you have to imagine is that there's this bulbous object coming out there, and then this one is actually kind of coming up out of the screen. I want you to just imagine that this is your universe. You live here. Could you go around and make maps? Could you take those maps, put them together into a big collection of maps and tell everybody where everything was? Now you know why we call this a thought experiment, right?
Is the top cut off?
Good question. That's an excellent question. And the answer to my question depends on the answer to that question, right? Does it stop? Okay, let's pretend that it doesn't stop. It keeps going. So your answer is, no, you couldn't do that. If it did stop, then your answer is, yes, you could do that. Okay, good. Hey, we're getting somewhere. I don't know where we're going, but we're getting there. Matter of fact, I kind of told you that you could do that. I didn't tell you, but I stole this picture, and this picture tells you there's a little map area here. You just map that one and put them all together. If it stops, then you're done. If it doesn't stop, then you're never going to be done. In topology, we're going to be looking for things that are called manifolds. So this is the topological version of what I was describing before as groups. In topology, they're looking for manifolds. A surface is called a 2-manifold if the local maps are 2-dimensional. Another way to say that is that the local map fits on paper. So let's just go back to the ones we were discussing. This map is theoretically an infinitely sized sheet of paper. The local maps are on paper. So this is a 2-manifold because every one of those maps is a 2-dimensional structure. What are the dimensions of the maps on this sphere? Well, just look at the picture I drew.
Two-dimensional as well?
They're 2-dimensional maps. And if the maps are 2-dimensional, then this thing is going to be called a 2-manifold. It's weird to call it that because it's not 2-dimensional. I'm not saying it's 2-dimensional. I'm saying that the local structure is 2-dimensional. What about this one? 2-dimensional maps equal a 2-manifold. All right, so I want you to stare at this example for a second and tell me what the local maps look like. And I'm not really asking what the local maps look like. I'm asking, are the local maps 2-dimensional? Maybe it's tough to imagine this after all the things I've put you through so far. So let me try just a visualization here. This is your universe. You live here. You can't go that way. You can't go that way. There's no such thing as this way or that way. You can go that way, you can go that way, that's it. So you make a map. That's your map. Is that map two-dimensional? No. If it's not two-dimensional, the thing that you're looking at is not a two-manifold. Okay, so hold on to that idea and answer the same question. Is the circle a two-manifold? No. Oh, you've all learned some topology. You can go home at dinner tonight and somebody say, well, what did you do today? I learned some topology. The circle is not a two-manifold. Now, somebody who's not a mathematician, tell me why the circle is not a two-manifold. I mean, you're correct. Just tell me why.
It's just a line?
The local structure is a line, right? If you just look at a point on the circle and look at the local structure, it doesn't look any different than that over there. If you're on it, I know you're saying, some of you are saying, well, it's curved. Hold on to that. So there are manifolds of just about any dimension you can imagine. We call them n manifolds, and the n isn't describing the dimension of the manifold. The n is describing the dimension of the local maps. So, let's look at the previous two examples. We said this is not a two-manifold because the local structure is not two-dimensional. But the local structure here is one-dimensional, and that makes it a one-manifold. Local structure here is how many dimensions? Single-dimensional local structure. That makes it a one-manifold. So these are not two manifolds, but that's not bad. It just means they're in a different class. They go into the one-manifolds. What's the theme? Topology is the study of surfaces. You want to know what points are on the surface? Those are called the elements of the surface. What does the surface look like near a point? Those are called the neighborhoods. You could also call those the local maps. And then is that surface different from other surfaces? And this is where you get to the classification. So I'm going to let you think about this for a couple minutes. Is it a manifold? I'll pretend that you're students in my classroom. Is it a manifold? Why or why not?
Depends on whether it meets in the center in a single point.
Let's pretend that it does.
Then it's not.
Why not?
Because you can't, one point has no dimension.
Let me just say something before I go any further. When I say why not, I'm not saying you're wrong. I have a pretty good poker face. What I'm really trying to figure out is, are you thinking the same thing that I'm thinking, or are they related? Or maybe you're looking at something different than I am, and I should have said, oh, wow, I didn't think of that before. So why were you saying that it's not?
Because it's a single point, it has no dimension in two things or in one.
Let me ask you a follow-up question. Are you looking at this point up here?
No, I'm looking at the middle point.
You're looking at the middle point. That middle point right there is different than all of the other points on this surface, right? If I'm down here and I draw a map, this picture is actually telling me that that map is going to be two-dimensional. But just imagine that this is your universe, and you get closer and closer to that point. There's a, oh my gosh, what's coming next feeling. Because you have this whole other thing on the other side, and when you get to that point, it's not a two-dimensional map anymore. You have maps going that way, that way, that way, that way. You need multiple, more than two dimensions to map that local area. It's not a two-manifold because of that point, and it's not, well, you say, okay, well, what's a one-manifold? A one-manifold means the local structure is one-dimensional. Well, the local structure here isn't one-dimensional. So it's not two, it's not one. Could it be three? Okay, let's talk about a three-dimensional not a three-dimensional manifold, a three-manifold. Three-manifold means the local mapping structure is three-dimensional. So I go to this spot up here, and I look at the local structure. Well, we already said it was two-dimensional. You don't need three dimensions for that. So I agree. It's not a manifold. So we marry the mathematical subjects into another subject called algebraic topology. In algebraic topology, our goal is to use algebraic structures like groups to help classify topological structures like manifolds. I have to be honest with you. Group is only one class of an algebraic object. Manifold is only one class of topological structure. There are other structures involved. I'm not telling you everything because we don't have all of time to do it. My only caveat with this is you can't just use any old algebraic structure that you want. There has to be a connection between the algebraic structure you're looking at and the surface itself. So we're going to go back to the one sphere. And on the one sphere, let me draw this in black here. We're going to highlight a point and just say you are here. Considering this in the context of what we were saying before, if you are here, you might want to map the local structure to figure out what's around you. If you had a map that went in this direction and then stopped and then went back, again, this is connected to something from last week. You can imagine that you're pulling a piece of string with you so you don't get lost. You pull that piece of string out to there to make your map. You say, okay, well, this is as far as I'm going to go because I don't feel like I want to go any further. And you come back. If you go out that far and you come back, you can actually reel in your string without having any obstacles. If you went further and stopped and came back, the same is true. The only time you really couldn't draw your string back is if you went all the way around. Now, why couldn't I draw my string back? You have to remember my idea is this is your universe. If you draw your string all the way around the circle back to where you started, your string is still there. You grab the other end. Now you have both ends of the string. You can't pull it through the center of that circle because there is no center. There's nothing there. It's not empty space. It's nothing. And you do have to distinguish between those. It's not empty space, because if it was, you could just pull it through. There's nothing there, as in nothing. Whoa. All right, I just want you to imagine you go all the way around that structure there, and then you get back to where you started, and you say, aha, that's where I started because I found the end of my string. I'm going to call that a loop. I'm going to call that loop L. Because I could, if I wanted to, loop and then loop again, which I think would be different than just looping once. I'd need twice as much string, right? So you could do 2 loops. Nothing stopping you from doing more, right? You could do 3, 4, etc. I'm not going to write any more down. What's the relationship between these objects here? Well, what I'm saying is I could perform a loop. I could do the same loop again, and I get another thing, whatever that thing is. If I put those two together, though, end to end, you're going to get that one. If I put those two together, end to end, you're going to get the next one over here, which I haven't written down yet. Which begs the question, well, what happens if I am here and I don't go anywhere? Now, I just want to imagine that that's a trip of no motion at all. There's no string involved. You're just standing in a place and you stay there. Okay, I'm going to call that another loop of some kind. That's my initial loop, in fact. That's my loop where I went out and came back and then I pulled the string in. Okay, so just imagine this. You're going to do a complete loop. And then you're going to go out and back and draw in that little string there. Is that different than this one? Maybe you need a minute to think about that one. I'll ask it again. I know it sounds like I'm in a hurry. We can stop this talk anytime we want. What I'm trying to, I get excited. That's why it sounds like I'm in a hurry. So I'm going to go all the way around the circle. That's my loop L. After I'm done with that, I'm going to go out on my map and then come back and then draw in the string. My question to you is that different than going all the way around and then just stopping there? It's almost like if you go out and then come back along that route, you should have just stayed where you were in the first place.
The final state is the same.
It's one of those things like, are you going to count that as time, distance, etc.? So let's say that that n is, you're not going to go anywhere. Here's another option. You could go that way. I'll even use a different color. You could start there, go the other direction, get back to where you started. Okay, you ready? You're going to start here. Going to go all the way around, that's L. You got to where you started, you're going to go all the way back. Can you imagine doing that with a piece of string? We have a piece of string, something back there. Some yarn. There's some yarn. There it is. There's your yarn. You take that yarn, you wrap it all the way around the circle, and you've got your loop. You can't draw your loop in because you've got that empty stuff in the middle there. There's nothing there. But then you're going to take that string, you're going to keep using more string, go all the way back the other way, get back to where you started. Could you draw that in? It takes more yarn, but you could pull it in now, right? By going all the way back, you've covered your trip again. And you could just pull it all the way back because you've already gone there, right? So doing a loop that way and then doing a loop that way, they cancel each other out. What am I trying to tell you? I'm trying to tell you that that's the opposite of your original loop. You could do that loop as many times as you want. And these loops, which are kind of backwards loops, they're going to cancel those loops. And if you put those loops end to end, it's like you don't go anywhere. So, just a quick review. If you go around 3 times, that way. Then you go around 3 times, that way. It's as if you never started. Okay, what am I talking about now? I'm not talking about topology anymore. I'm back into algebra. You're talking about 1, 2, -1, -2, -3. Those are the integers. That's called a loop group. And we summarize all of that information by saying that the loop group of the circle is isomorphic to the integers. I can't say that it is the integers because it is a collection of loops. But I can think of each of those loops as being represented by a number. That number is how many times did you go around this way. The negative of that is just go the opposite direction. So it turns out that this loop group, it's not unique to this circle, but if you had a topological structure that had a different loop group, then it's a different topological structure. Let's compare that with the loop group of the line. Oh, there it is. Loop group, you have to have a loop. Your loop means you're going to start wherever you want. I don't care where you start. You're going to go out into your structure somewhere. You have to come back. So I start here, I go out, I come back. Could I draw that string in? I sure could. If I go the other way, come back, could I draw that string in? So ultimately what we're seeing is I could create loops, but you can't leave the line. If you leave the line, you're outside of your surface, you're no longer in that space anymore, and you're talking about a different space. That is my space. If this is my only space, I have to stay on that line, and I have to come back to where I started. So I go out, I come back, I can draw in any loop that you can make on this space. So there really is only one loop, and that loop is, don't go anywhere. Doesn't really sound like a loop because you're not moving, but any loop that you do make could be contracted back to that point by drawing in the string. So we say the loop group of the line is trivial. That sounds very formal. When I say it's trivial, it just means that the loop group only has one element. I do need to be honest with you. Sometimes, in some very interesting topological spaces, the loop group does depend on where you are. So your base point of operations is going to matter. For the circle, it doesn't matter. You can have your "you are here" sign anywhere on the circle, and it's not going to change the loop group. Okay, so the last thing I want to say about that is we do have to distinguish between loops and elements of the space. They're related. In fact, a loop is a collection of those points, but the loop and the points are separate things, right? The loop is a collection of points in a sense. Okay, here's your thought experiment, your next thought experiment. Your space is now the two-sphere. You can't leave it, but you can go anywhere on it that you want. You're going to fix your "you are here" sign maybe up here at the North Pole. There you are. And you want to go out and start making loops. What's the loop group? Is it like this one?
No.
Why not?
Because you can go anywhere. You
I could go anywhere, that's true.
infinite directions.
And you can always pull your string in.
That's the question we're really asking, right? Could you draw the string in? Because if you can draw the string in, you might as well just not go on your loop. There is a rule about loops. You have to go back to where you started. So you're going to start at the North Pole. You have to go back to the North Pole.
And you can go this way or that way or this way or that
True.
way. Look like a ball of yarn all wound up.
What were you saying, Renee?
Well, when you're on a sphere, whenever you're pulling your string, it can slide over eventually.
So you could potentially go any direction that you wanted to from the North Pole. You always have to come back, and you can always draw that string in. So in fact, even though this topological structure looks a lot different to us than this one, the loop groups are the same.
I only know that from last
Oh, I can't make you unlearn the things that you've learned. Anyway, so the loop group of the two-sphere is trivial. Here's an example of a topological surface whose loop group is very non-trivial. You could put your "you are here" sign right here in the middle. I'm just thinking of this as the surface, okay? So this is all empty in the middle. You could start here and go around there. You can't draw the string. You can start here and go around there. Can't draw on that string, can't draw on that string. There are lots of loops in there that are non-trivial. And some of them are different than the other loops. So this is an example of a topological surface that has multiple independent, non-trivial loops. I don't know how many times I could say that fast. So let's try an attempt at who cares. If I start with two one-spheres and include the interiors, I can build something from this that's actually relatively familiar in the context of today's discussion. So previous to this slide, you weren't allowed to go inside the sphere. So we're going to talk about, well, what happens if you are? So you're going to start with a disk. It's actually easier to visualize this if the two disks are above and below. So this is the difference between a disk and a sphere. The disk, you're allowed to go inside. So the disk has all this stuff in here. You're going to go there, you're going to make your map. And you're going to go over here and you're going to make your map. And these do have boundaries on them. So if you get out here to the edge, you can make a map, but you can only make a map that's inside that disk. So you can imagine that this particular disk is mappable in a finite sense. Like I can put a map on each one of those points, put all the maps together. I've mapped the whole thing. If you can believe it for this one, then you can probably believe it for this one because they're just the same shape drawn twice. What we want to do now, though, is imagine that this point here is that point there. And that this point here and this point here, they're not different. They're the same. And it's not that I made a mistake. I just didn't tell you that. Because I was trying to draw my maps. So where is this point here? Well, that point has a mirror image down here. So it's like these maps are connected. And you can imagine taking this map and bending it so you kind of turn it over, take them, put them together, and you want to separate these because the points inside the disks are not the same, and that's what you get. You have a map for the top, you have a map for the bottom, you put them together, and you get a map for the sphere. So you can take these two-dimensional objects, which are two manifolds, put them together and get a three-dimensional object, which is still a two-manifold. Why is it a two-manifold? Can anybody remind me? Well, why isn't it a one-manifold or a three-manifold? It's because of the local maps. The local maps tell you the dimension. So this one, the local maps are two-dimensional. So maybe you think I'm kidding. Here's an example of a projection. This is a Mercator projection. But the thing that you'll notice about this picture, it's not even a picture, this thing, is that the bottom is white and the top is white. Now, if nobody gave me instructions on how to put this map together, maybe I think that white goes with white. Is that where we live? Now here's the thing that you have to remember. This is like you were taught this from a long time ago that this is where you are. But if I didn't know that and I just looked at the picture, maybe I made the mistake of putting the white with the white and I get this thing. Then I look on the edges of this thing. Okay, the edge over here is blue and the edge over here is blue. Say, oh, well, I'm really supposed to put those together. And that's where, oops. Well, you get the idea. Maybe that's where you live. So I guess what I'm saying with that is that the maps you create locally are important. I've already answered the question of how you put them together. It also is important. It's not just making the maps, but how do you put them together? So let's put some conclusion on this discussion. It seems to me possible that we live in a three-manifold. What I mean by that is you go out into space. This is a two-dimensional representation of space. This is a picture from NASA. You go out into space. You are here. You start making maps of the local area. The map that you make of the local area is three-dimensional. Right? You have up, down, left, right, and up, down, left, right, forward, and back. There you go, 3 dimensions. The question might be then, what is that manifold? Is that manifold going to have a trivial loop group? Is that manifold going to have a loop group that's isomorphic to the integers, or maybe one of those finite groups we saw at the beginning? Oops, that's the wrong direction. You can actually build what we call the three-sphere by using 2 spheres. The process is almost identical to this one over here. Instead of starting with 2 disks, you start with 2 balls. Now, ball is a difference from a sphere. Ball includes the middle part. So, you live in the center of that ball. You map the area around it. You got your nice 3D map. And you start mapping the whole thing. You map the whole ball. And then you realize, oh, wait a minute. This point here is that point there. I was looking at 2 different maps, but they're mapping the same region. And I can actually get from this ball into that ball just by going across that point. So imagine you draw a loop from this ball into that ball, and you go back into there. Could you draw on your string? You are here. You go over to that ball, you come back. You could. Matter of fact, what happened with that construction over here? Just think about this. We started with 2 disks. They have boundaries. You put them together. You get that sphere. The sphere doesn't have a boundary. So you started with things that do have boundary. You put them together and you don't have boundary anymore. That's kind of like what happened on the projection of that map. If you put the map together properly, you get that sphere. The sphere doesn't have boundary, although if you keep going in one direction, eventually you get back close to where you started. So, brief history lesson, and we're out of time, so I'll tell you the history quickly. In the mid-19th century, Bernard Riemann was the first person to really disaggregate topology from geometry. And what he said was that in topology, we are going to study the surface without mention of distance. The way that you measure distance does determine something, but you can actually talk about the surfaces themselves without discussing distance whatsoever. He allowed for multiple geometries on a single space. So you might have one space of points with multiple different geometries on the same space. Felix Klein is considered to be perhaps a successor of Riemann in the sense he kind of worked in the same general area. One of the things that he did was define topology. He said, this is what we're really studying here. And he laid out a path. If you follow this path, you will have a pretty good understanding of what topology is. Now, he didn't actually do all of that because it was new at the time, and he couldn't do it all at the same time. Around the same time as Klein is doing all this in Germany, there's another mathematician in France by the name of Henri Poincaré who actually creates and discovers the foundations of topology independent of what's happening in Germany. So in Germany, you have these people that are working on this problem. Poincaré actually develops it kind of underneath their feet without their knowledge. He publishes his information in some journals, and he starts having communication with Klein back and forth. It's really kind of an interesting battle how they discuss this. But anyway, in 1904, Poincaré suggested it might be important to know if there is another a finite three manifold with trivial loop group. Now I'm just talking about the three sphere as one of those objects. He wants to know, is there another one? And the answer is no. Richard Hamilton in 1982 invented what we call the Ricci flow. And he connected the Ricci flow, I shouldn't say he invented it. Anyway, he connected the Ricci flow with Poincaré's conjecture and said, if we're able to do something on the flow, then we can do something with the conjecture. It wasn't until, in 2000, the Clay Mathematics Institute publishes a list of what we call millennium problems. If you solve one of these problems, you make $1 million. So Gregory Perelman solves the Poincaré conjecture in 2002, 2003. And rather than getting his research published in a journal, which is what was happening in the 19th century and the early 20th century, he just uploads it to the internet. Doesn't even tell anybody about it. Somebody's reading papers and he sees this Perelman name attached to it. He says, what is that guy doing? He looks at the papers, he realizes this guy has solved the Poincaré conjecture. He has proved that there is only one finite three manifold that has a trivial loop group. He wins the Fields Medal in 2006. There is no Nobel Prize in mathematics. This is our version. He says, I don't want it. He wins the Clay Mathematics Prize, $1 million, and he doesn't want that either. So I'll leave you with a quote. Looking up at the night sky and the distant stars and galaxies and clusters of galaxies, it is inconceivable to me that there are not other intelligences out there, some far different from us. Hundreds of years hence, if we ever develop technologies that will enable us to meet and to communicate, we will discover that they will know, or want to know, that the only finite three manifold with trivial loop group is a three sphere. Count on it. Anyway, here's